In differential geometry, a G-structure on an n-manifold M, for a given structure group G, is a G-subbundle of the tangent frame bundle Fm of M. The notion of G-structures includes many other structures on manifolds, some of them being defined by tensor fields. For example, for the orthogonal group, an O structure defines a Riemannian metric, and for the special linear group an SL structure is the same as a volume form. For the trivial group, M.The structure consists of an absolute parallelism of the manifold. In mathematics, in particular the theory of principal bundles, one can ask if a principal bundle over a group comes from a subgroup of. This is called reduction of the structure group. Several structures on manifolds, such as a complex structure, a symplectic structure, or a Kähler structure, are G-structures with an additional integrability condition. Principal bundles and G-structures. Although the theory of principal bundles plays an important role in the study of G-structures, the two notions are different. A G-structure is a principal subbundle of the tangent frame bundle. But the fact that the G-structure bundle consists of tangent frames is regarded as part of the data. For example, consider two Riemannian metrics on Rn. The associated O structures are isomorphic if and only if the metrics are isometric. But, since Rn is contractible, the underlying O bundles are always going to be isomorphic as principal bundles because the only bundles over contractible spaces are trivial bundles. This fundamental difference between the two theories can be captured by giving an additional piece of data on the underlying G-bundle of a G-structure. The solder form. The solder form is what ties the underlying principal bundle of the G-structure to the local geometry of the manifold itself, by specifying a canonical isomorphism of the tangent bundle of M to an associated vector bundle. Although the solder form is not a connection form, it can sometimes be regarded as a precursor to one. In detail, suppose that Q is the principal bundle of a G-structure. If Q is realized as a reduction of the frame bundle of M, then the solder form is given by the pullback of the tautological form of the frame bundle along the inclusion. Abstractly, if one regards Q as a principal bundle independently of its realization as a reduction of the frame bundle, then the solder form consists of a representation ρ of G on Rn and an isomorphism of bundles theta. Trademark Q times ρ Rn. Integrability conditions. Several structures on manifolds, such as a complex structure, a symplectic structure, or a Kähler structure, are G-structures with an additional integrability condition. Without the corresponding integrability condition, the structure is instead called an almost structure, as in an almost complex structure, an almost symplectic structure, or an almost Kähler structure specifically. A symplectic manifold structure is a stronger concept than a G-structure for the symplectic group. A symplectic structure on a manifold is a two-form omega on M that is non-degenerate. Together with the extra condition that d omega equals 0, this latter is called an integrability condition. Similarly, foliations correspond to G-structures coming from block matrices, together with integrability conditions so that the Frobenius theorem applies. Isomorphism of G-structures. The set of diffeomorphisms of M that preserve a G-structure is called the automorphism group of that structure. For an O structure they are the group of isometries of the Riemannian metric, and for an SL structure or volume-preserving maps. Let P be a G-structure on a manifold M, and Q a G-structure on a manifold N. Then an isomorphism of the G-structures is a diffeomorphism Fmn such that the push-forward of linear frames F** Fm restricts to give a mapping of P into Q. The G-structures P and Q are locally isomorphic if M admits a covering by open sets U and a family of diffeomorphisms φ UFN such that φ induces an isomorphism of P, U, Q, F. An automorphism of a G-structure is an isomorphism of a G-structure P with itself. Automorphisms arise frequently in the study of transformation groups or geometric structures. Since many of the important geometric structures on a manifold can be realized as G-structures, a flat G-structure is a G-structure P having a global section consisting of commuting vector fields. A G-structure is integrable if it is locally isomorphic to a flat G-structure. A wide class of equivalence problems can be formulated in the language of G-structures. For example, a pair of Riemannian manifolds are equivalent if and only if their bundles of orthonormal frames are isomorphic G-structures. In this view, the general procedure for solving an equivalence problem is to construct a system of invariants for the G-structure which are then sufficient to determine whether a pair of G-structures are locally isomorphic or not. Connections on G-structures. Let Q be a G-structure on M. A principal connection on the principal bundle Q induces a connection on any associated vector bundle, in particular on the tangent bundle. A linear connection on trademark arising in this way is said to be compatible with Q. Connections compatible with Q are also called adapted connections. Concretely speaking, adapted connections can be understood in terms of a moving frame. Suppose that phi is a basis of local sections of trademark which defines a section of Q. Any connection determines a system of basis-dependent one-forms omega via x phi equals omega ij vj where, as a matrix of one-forms, omega 1 gl. An adapted connection is one for which omega takes its values in the Lie algebra G of G. Torsion of a G-structure associated to any G-structure is a notion of torsion, related to the torsion of a connection. Note that a given G-structure may admit many different compatible connections which in turn can have different torsions. But in spite of this, it is possible to give an independent notion of torsion of the G-structure as follows. The difference of two adapted connections is a one-form on M with values in the adjoint bundle A to Q. That is to say, the space AQ of adapted connections is an affine space for omega 1. The torsion of an adapted connection defines a map to two forms with coefficients in trademark. This map is linear. Its linearization is called the algebraic torsion map. Given two adapted connections and their torsion tensors T differ by tau. Therefore, the image of T in coca is independent from the choice. The image of T in coca for any adapted connection is called the torsion of the G-structure. A G-structure is said to be torsion-free if its torsion vanishes. This happens precisely when Q admits a torsion-free adapted connection. Example: torsion for almost complex structures. An example of a G-structure is an almost complex structure, that is, a reduction of a structure group of an even-dimensional manifold to GL. Such a reduction is uniquely determined by a C-infinity linear endomorphism J and such that J2 equals -1. In this situation, the torsion can be computed explicitly as follows. An easy dimension count shows that, where omega 2, 0 is a space of forms B omega 2 which satisfy therefore, the torsion of an almost complex structure can be considered as an element in omega 2, 0. It is easy to check that the torsion of an almost complex structure is equal to its Nying-Hewish tensor. Higher-order G-structures. Imposing integrability conditions on a particular G-structure can be dealt with via the process of prolongation. In such cases, the prolonged G-structure cannot be identified with a G-subbundle of the bundle of linear frames. In many cases, however, the prolongation is a principal bundle in its own right, and its structure group can be identified with a subgroup of a higher-order jet group, in which case, it is called a higher-order G-structure, Kobayashi. In general, Cartan's equivalence method applies to such cases.